Hello students, welcome to class 12 physics. In this video we are going to obtain the relation of the voltage applied to a series LCR circuit. So here L stands for inductor, C stands for the capacitance, R stands for the resistance. So in this circuit the inductor, capacitor and resistor, all the three are connected in series, and with these series combination AC voltage is applied. So below shows a series LCR circuit connected to an AC source. Voltage of an AC source is V equals to Vm sin omega t. So here is the AC source and the resistor, capacitor, inductor, all these three are connected in series. Now in this circuit we are going to apply the Kirchhoff voltage law. So let us first choose the path. So this will be the path and this is the current direction. So let us start with this AC source. So AC voltage, that is V. Now because the path and the current direction both are same, we will take negative sign. Then voltage developed across the resistor, that is VR. Again now the current direction and path are same, so sign will be negative. Voltage developed across the capacitor, that is VC. Again path and current direction both are same, so sign will be negative. Now the voltage developed across the inductor, that is VL. So again now we go forward, we will be having the AC source. So here the circuit is completed. So it is equals to 0. Now taking this minus VR, minus VC and minus VL on the other side, we can write the equation as V equals to VR plus VC plus VL. So this is the equation. V equals to VL plus VR plus VC. And the voltage that is along the inductor, voltage drop along the inductor, that will be equals to L di by dt. This we have already discussed in the previous theory, that is the AC voltage applied to the inductor only, as well as VR equals to IR, and voltage across the capacitor, that is VC, equals to Q by C. So substituting that, we get V equals to L di by dt plus IR plus Q by C, where potential difference across the ends inductor equals to L di by dt, potential difference across the ends of capacitor equals to Q by C, and potential difference across the ends of the resistor is equal to IR. So students, up to here first you note down, and then we will be seeing the relation between the voltage and the current in the given circuit. So first note down this. Let us see the relation of the phase between instantaneous current and the voltage with the help of a phasor diagram for series LCR circuit. So in the circuit LCR is in series. Therefore, the AC current in each element is the same at any time, having the same amplitude and phase, because we know that for the series combination the current passing through that will be same. So here let it be I equals to Im sin omega t plus phi, where phi is the phase difference between the voltage across the source and the current in the circuit. Let I be the phasor representing the current in the circuit, and VL, VC, VR and V represent the voltage across the inductor, resistor, capacitor and the source respectively. VR is parallel to I. Here VC is pi by 2 behind current. This we have already discussed in the theory, AC voltage applied to the capacitor. and VL is pi by 2 ahead of current. That is, in the AC voltage applied to the inductor, voltage is leading the current by pi by 2. So VL, VC, VR and I are shown in the figure with appropriate phase relation. So here we can draw the same diagram like this. Here we are having the V vector and here will be VC. In the upward direction there will be VL. Here it makes an angle omega t plus phi. There will be 90-degree angle between VR and VL. So the amplitude of phasor are as follows. VRM equals to IMR. We have discussed the equation, that is the maximum voltage for the resistor, that is equals to IMR. The maximum voltage for the capacitor, that is equals to IMXC, because here we are applying the Ohm's law, that is V equals to IR. And here we have already discussed that the reactance is also having the same function as that of the resistance. The function of the resistance is to limit the current or to oppose the current. The same function is of the reactance, whether it is the capacitive reactance or the inductive reactance. It will be limiting the current. So for the capacitor, Vm equals to IMXC, where X is capacitive reactance. For inductor, Vm equals to IMXL, where XL is the inductive reactance. So the equation that is VL plus VR plus VC equals to V, where VL equals to LdI by dt, VR equals to IR and VC equals to Q by C. This relation is represented in figure below. So here you can see that the VR makes an angle omega t with respect to this axis, that is omega t, that is considered as the maximum voltage. When you take the projection on the y axis, that becomes VMR, that is VR, and from that when you take the 90-degree angle, the vector that is VC plus VL. Since VC and VL are in opposite direction, so the resultant value of phasor VC minus VL equals to VCM minus VLM. Since V is represented as the hypotenuse of the right angle triangle whose sides are VR and VC plus VL, Pythagorean theorem gives you, let us draw this figure again, taking here VR, taking its projection over here, here it will be VC minus VL, here we are having VR. So from this diagram, let us give it the name A, B and C. From this triangle ABC, let us apply the Pythagoras theorem. So here Vm square that is this vector Vm square is equals to Vc, because this side and this side both are same, so we can say Vc minus Vl whole square plus Vr whole square. So Vrm square plus Vcm minus Vlm whole square. Now substituting its formula, Vrm is nothing but Imr, so Imr whole square plus Vcm is nothing but Imxc and Vlm is nothing but Imxl. So substituting the formula, we get Vm square equals to, taking Im square common, we get Im square into bracket r square plus xc minus xl whole square. Here we need to find the current, so taking current as the subject and taking this term on the other side, we get Im square equals to Vm square upon r square plus xc minus xl whole square. Taking root on both the sides, we get Im equals to Vm upon under root r square plus xc minus xl whole square. Now we know by Ohm's law that I equals to V upon R, where R is what? That is the resistance. Its function is to limit the current. But here we are having not only resistance but resistance plus the reactance, because we are having capacitive reactance as well as the inductive reactance. But the function of this whole term is to limit the current. So giving that term as Vm by Z, where Z is called the impedance and impedance is equal to resistance plus reactance. So the equation can be written as Im equals to Vm upon Z. Im is the maximum current, so you can consider that as the amplitude of the current. Since phasor I is always parallel to the phasor Vr, the phase angle phi is the angle between Vr and V can be determined from the figure. So you can see over here. Here if we draw the same figure in terms of just the resistance, reactance and impedance, this vector becomes impedance. Over here we were having Vc minus Vl, so just writing its reactance, that is Xc minus XL, and here we were having Vr, so just writing its resistance, it will be R. So from this we can write, from this figure, tan phi equals to Vcm minus Vlm upon Vrm. Writing its formula, we get Im Xc minus Im XL upon Im R. Taking Im common in this and cancelling out the Im, we get tan phi equals to Xc minus XL upon R. This gives the phase angle. Impedance Z of the circuit can be determined by the figure. This is called impedance diagram, which is a right triangle with Z as its hypotenuse. Impedance from impedance diagram, that is Z equals to under root R square plus Xc minus XL whole square. So students, you may note down this theory.